So in this screencast, we are going to talk about naming covalent compounds or molecular compounds, and we're going to talk about electronegativity and polarity. When we name molecular compounds, the first step is to identify that's what you're naming. And the easiest way to do that is to say, look, these are nonmetals. Now, you also need to understand that molecular compound, there's a synonym for that, and that's also known as a covalent compound. So molecular compounds, these consist of nonmetals and no charge. So sometimes students confuse those with polyatomic ions because there's a charge. There's no charge here. So for example, right, if we are looking at SO3, this is a covalent compound. Two nonmetals are here. And the first word is the name of the first element in the formula. So sulfur. The second word, you change the ending of the second element to IDE, oxide. Now, this is nothing different than ionic nomenclature so far. But here's the deal. We need to tell how many atoms are in each one here. And so we use prefixes. And so that's why there's a trioxide here. There is an exception, and the exception to using these prefixes, if it's the first element is a singular element, you don't say monosulfide, sulfur trioxide, you say sulfur trioxide. Similar to using sodium chloride with ionic compounds, I always used to think of carbon dioxide. This is something you're probably pretty familiar with, right? And it's CO2. And this would help me remember the rules for naming. So I would write this on my periodic table. And I would say, look, here, there are two nonmetals. The first one gets the element name. The second one, you change the ending to IDE. We're going to use prefixes. There are two of those. That's di. And then the first element, if it's all by itself, doesn't have the mono there. Here are the prefixes, mono, di, tri, tetra, penta, hexa. So if you notice this 6 is a hexagon, hepta, octa, octopus have 8 legs, nona, and deca. So those are the prefixes that we're going to use. Now, here are kind of the two big exceptions. Do not use the prefix mono when naming the first element. We talked about that on the previous slide. And then prefixes ending with an O or A are modified when used with elements beginning with vowels. So P4O10, that's tetraphosphorus dec oxide. It's not deca oxide. So we get rid of the A there, which is crossed out, just because that cross out is kind of weird. Right? That is how we would name it. So I find the naming of these to be a lot easier than ionic compounds. There's no Roman numerals and no polyatomic ions. This is it. Okay. Now, however, there are two types of covalent compounds that we're going to run into. We can have polar covalent compounds, and we can have nonpolar covalent compounds. And so let's talk about those and how we recognize them. So through the chapter, I've kind of acted like there's a clear distinction between covalent and ionic bonding. But in reality, there really isn't a super clear distinction between ionic and covalent bonding. It's more of a gradual transition from pure covalent to pure ionic. And so, for example, you can see some examples of what we would consider non-polar covalent here, polar covalent here, and then ionic here. The color bar indicates the relative charge distribution from one end of the molecule to another. So if one end is really electron poor, right, which would make sense, sodium's given up an electron, so he's electron poor. And then chlorines gain that electron, so it's electron rich. And you can see there's a big difference there, right? And that's kind of ionic. But I want you to zoom in and look at Cl2 and HCl. What you find is Cl2, that's pretty uniform here in the middle. It's like they're sharing really well. So that's an even charge distribution. They're sharing those electrons well. If you come over here and you look at polar covalent, a lot of that electron density is over here on the chlorine, right? And that makes that chlorine a little bit negative and this hydrogen a little bit positive. And so a lot of times we will represent this with a lowercase delta, delta negative, and then lowercase delta positive. We'll say like partially positive or partially negative. So let's give some definitions to these. If you have when we talk about this, we're talking about bond polarity. And this is just a measure of the extent to which bonding electrons are unequally shared due to differences in the electronegativity. So we're going to talk about electronegativity on the next slide of atoms. Okay. And so a polar covalent bond is unequal sharing of a bonded pair of electrons between atoms. So it's an unequal sharing of a bonding pair of electrons between atoms. Now this results in an uneven distribution of charge. So how do we figure out if things are nonpolar covalent or polar covalent? And why is it important? Well, it's important because it helps us predict properties, right? And so we are going to rely on using this to predict properties in future chapters. The way we identify it is we can identify it by using a periodic trend called electronegativity. So electronegativity is the ability of an atom to attract electrons in a bond to itself. And we have numbers that are assigned here. A scientist named Linus Pauling developed this concept of electronegativity to explain bond polarity. And what you'll see is that electronegativity increases as you go from left to right on the periodic table, and that it increases up a group. Now, notice the noble gases aren't on here. They're not reactive, so we just leave them off. And then fluorine here is the most electronegative and is given an arbitrary value of 4, okay? Now, you do not have to memorize these values. Please do not. If you have to do anything, if you have to calculate the electronegativity of a bond, I will give you these values. So one way we can figure out if a bond is polar or nonpolar is to calculate the electronegativity difference. So we can calculate the electronegativity difference. And the way that we do that is, well, let's figure out what the numbers mean. Let's talk about the numbers. If the difference in electronegativity, and I'm going to represent that with delta E, right, is less than 0.5, that bond is nonpolar. Okay. If the delta E is between 0.5 and 2, that is a polar covalent bond. Ooh. And let me go back and clarify. This is a non-polar covalent bond as well. Okay. And then if the delta E is greater than 2, that's considered ionic. So you look at these for the different bonds. So for example, if we had a hydrogen bond for like this, 2 hydrogens were bonded together, we would say, okay, 2.2. So I come over to the table, I see 2.2, or it's given to me, minus 2.2, and that's 0. And so that is a nonpolar covalent bond. Okay. Anytime you have 2 atoms that are the same thing, you are going to end up with a nonpolar bond. Okay. Then you can see things like carbon and hydrogen. Okay. These values are different. Carbon is 2.6 and hydrogen is 2.2. When you're calculating the difference between them, always put the bigger number first. And so that's going to be 2.6 minus 2.2, and that gives 0.4. And so that's still nonpolar. Then you have a Cl and an H. And so when we look at this, 3.2 minus 2.2, and that's 1.0, and that's polar covalent. All right. Now, I want us to look at an example of something that's ionic, and we've looked at sodium chloride a lot with ionic bonding. If we go through and do this calculation here, it's 3.2 minus 0.9, and that gives us 2.3, and that's greater than 2, and so that's ionic. So these values can be used to predict whether things are nonpolar covalent or bonds are polar covalent and nonpolar or ionic. Now, when we talk about polar bonds, right, sometimes you don't have a chart. And so the degree of polarity depends on the differences in electronegativity. And so it's really helpful, for me at least, to be able to visualize this, right? And there's a couple ways you can visualize it. One way to visualize it is by looking at a battery, right? We know that chlorine is farther over on the periodic table. Hydrogen is there. They're very far apart. They're going to have a big difference in electronegativity, even without looking at the numbers. And so we can see that chlorine, with all of its extra electrons there, is going to be partially negative. And so we get that delta minus from that partial negative. And then we've got a partial positive here. You can also represent this with an arrow like this. And in that arrow, the direction of polarity is indicated by the arrow pointing to the more negative end of the bond. All right. And then generally the positive sign, so if you look here, there's a positive, it's towards the more partially positive end. I like to view this as a tug of war. And so, for example, if we look at here's HCl, and basically I like to view it as they're fighting over electrons, and the chlorine's stronger. And so the chlorine can pull the electrons closer to him because he's so much stronger, right? So that's how I like to view it. When we talk about a nonpolar bond, right, that is an equal sharing of electrons. And so it's like a tug of war where two people are the same strength, right? And so they're going to share these electrons equally. Now, we've talked about just looking at bonds, and in the next chapter, in the next screencast, we are going to talk about electron geometry, which is going to be able to help us identify polar molecules and nonpolar molecules. And when we're identifying nonpolar molecules, it's almost easier to identify nonpolar molecules than polar molecules at the beginning. Nonpolar molecules kind of fall into three categories. The first category is if it's all the same element. It is a nonpolar molecule, right? Because we talked about bonds, but now we're here with molecules. So like H2, Cl2, S8, that's sulfur. If it just has carbon and hydrogen, this is called a hydrocarbon, right? You see this in organic chemistry. If it's a molecule and it's just carbon and hydrogen, no matter how big it is, right? If it's just carbon and hydrogen, it's a hydrocarbon, it's nonpolar. And then the third type, which we're going to get into in some future screencasts, like one or two down, is if there is symmetry. And so to be able to identify nonpolar molecules from polar molecules, and then to be able to identify their chemical properties and make predictions, we have to understand if there's symmetry in the molecule. And so we have two tools to help us with that. One are Lewis structures, and then valence electron shell repulsion theory, which is abbreviated as VESPER. And that's going to help us figure out if there's symmetry in the molecules and they're nonpolar or polar, and that's going to help us predict their properties when we get into solution chemistry. If you have any questions about this, please feel free to pop by my office and ask. I love answering questions, and I would be happy to help.